Welcome to the course on an introduction to information theory. So in this lecture we are going to solve some problems related to channel capacity computation. So in problem number 1, we are going to compute capacity of this discrete memoryless channel. So you can see this channel has two inputs 0 and 1 and 8 outputs which are given by 0, 0 dash, 0 double dash, 0 triple dash, 1 triple dash, 1 double dash, 1 dash and 1. So these are the 8 outputs of the channel and these are the 2 inputs to the channel. The channel transition probabilities are given here. So probability of 0 given 0 is 0.309, probability of 0 dash given 0 is given by 0.191, and similarly you can see the transition probabilities are given here. The first question is, find the capacity of this channel. So first we will try to see whether this is a symmetric channel or not. So clearly this is not a strongly symmetric channel because you can see this is not uniformly, it's not uniformly focusing. For example, if you consider this particular output, the probabilities are 0.309 and 0.006, but if you consider this output, the transition probabilities are 0.191 and 0.017. So clearly this is not a strongly symmetric channel, but we need to see whether this is a symmetric channel, whether we can decompose this channel into strongly symmetric channel. So let's look at this output 0 and output 1. If you look at the probabilities, this is in the decreasing order, this is 0.39 and this is 0.006. What about this particular output? Again the probabilities, transition probability is 0.309 and 0.006. 309 and 0.006, which means 0 and 1 have the same focusing. Let's look at 0 dash and 1 dash. This is 0.191 and what about this? This is 0.017. Similarly this one is 0.191 and this is 0.017. So these two are also uniformly focusing. Similarly look at 0 double dash and 1 double dash. This is 0.191 and 0.044 and this is also 0.191 and this one is 0.044. And finally these two also have same focusing. You can see this is 0.150 and this is 0.092 and 1 triple dash is 0.150 and this is 0.092. So you can see now that we can decompose this output into 4 uniformly focusing set, one corresponding to these two, one corresponding to these two, then one corresponding to this and one corresponding to this. So to compute the capacity, we will first try to decompose this into strongly symmetric channel. So if we try to do that, as I said, 0 and 1 they have same focusing, 0 dash and 1 dash has same focusing, 0 double dash and 1 double dash has the same focusing, and 0 triple dash and 1 triple dash have the same focusing. Now if I decompose the same channel into 4 such strongly symmetric channel, I can write the equivalent decomposed channel in this particular fashion, where I am selecting this channel consisting of output 0 and 1 with selection probability Q1. I am selecting this channel which gives output 0 dash and 1 dash with selection probability Q2. I am selecting this channel which gives output 0 double dash and 1 double dash with selection probability Q3, and similarly I am choosing the fourth channel with selection probability Q4, and each of these individual channels are binary symmetric channels. So I am just writing this crossover probability as epsilon 1, epsilon 2, epsilon 3 and epsilon 4. Similarly these probabilities are 1 minus epsilon 1, 1 minus epsilon 2, 1 minus epsilon 3 and 1 minus epsilon 4. Now the first thing that I need to do is to find out the value of Q1, Q2, Q3, Q4 and epsilon 1, epsilon 2, epsilon 3 and epsilon 4. Now how do I find out these values? So I am just going to map these transition probabilities. So if you look at, let's say, transition probability from, so transition probability of 0 given 0, what is this in this diagram? It is given by Q1 times 1 minus epsilon 1, that's this. And if you go back to this diagram, the transition probability of 0 given 0 is given by 0.309. So what we can do is we can write Q1 into 1 minus epsilon 1 is equal to 0.309. Similarly, what is the transition probability of 1 given 0? That is given by, from this diagram, this is Q1 times epsilon 1, that is this. And let's go back to original. What is the transition probability of y1 given 0? That is 0.006. So Q1 epsilon 1 is 0.006. I have two equations and two unknowns, Q1 and epsilon 1. So I can solve them to get Q1 and epsilon 1. So I get epsilon 1 to be equal to this and Q1 to be this. I follow exactly the same procedure to get Q2 epsilon 2, Q3 epsilon 3, Q4 epsilon 4. I am just writing it here. We can do it once more. Let's see. Look at transition probability of, what's the probability of O dash given O? 0. 0 dash given 0, that is given by Q2 times 1 minus epsilon 2, that is equal to Q2 times 1 minus epsilon 2, and this is nothing but, if we go look at the original figure, probability of O dash given O is 0.191. So this is equal to 0.9191, and that's what we have written here. Similarly, we can write this and solve for epsilon 2 Q2. It's exactly the same procedure that we did to find Q1 and epsilon 1. We can repeat this process to get Q3 epsilon 3. So this is the value of epsilon 2 Q2, this is the value of epsilon 3 Q3 that we get following the same procedure, and this is the value of epsilon 4 and Q4 that we get. So now that we have the selection probabilities of each of these 4 strongly symmetric channels, and each of these channels are binary symmetric channel, which is a strongly symmetric channel. So we know the expression for capacity for each of these channels. So then the overall channel we can capacity we can write as summation of capacity of each of these strongly symmetric channel multiplied by their selection probability. So if we sum that up, we get the capacity of a symmetric channel. So, and what is the capacity of each of these channels? These are a binary symmetric channel, so its capacity of binary symmetric channel is given by this. Okay, so we plug that value in here. We know what is epsilon, we know this, we know what is Q1, so we can calculate the overall capacity of this channel, and this comes out to be 0.477 bits. In the next question, what we are saying is, if we use a hard decision demodulation, then we would combine these 4 output symbols into one symbol, call it 0, and we would combine these output symbols into an output symbol, let's call it 1. Now I'm asked, so that would then result in a binary symmetric channel. So this question asks, what is the capacity of the resulting binary symmetric channel if you combine all these inputs 0, 0 dash, 0 double dash, 0 triple dash into one output 0, and do the same thing with this 1, 1 dash, 1 double dash and 1 triple dash. So the resulting channel would be something like this. So you have 2 inputs 0 and 1, and you will also have 2 outputs 0 and 1. And what are these transition probability? What's the probability of getting 0 given input is 0? That would be probability of equal to probability of 0 getting 0 plus probability of 0 dash given 0 plus probability of 0 double dash given 0 plus probability of 0 triple dash given 0. So that would be this probability, and similarly we can compute the other probabilities as well. So the resulting channel that we'll have is given by this, and this crossover probability, as I said, is given by probability of 0 given 1, probability of 0 dash given 1, probability of 0 double dash given 1, and probability of 0 triple dash given 1. So if we add them up, we get epsilon to be this. Now this is a binary symmetric channel, so its capacity will be given by 1 minus binary entropy function of epsilon. So this is nothing but this many bits. Okay. Now if you compare this capacity to the capacity that we computed for the original channel capacity was 0.477 bits per use, whereas capacity of this channel is 0.368. So as you can expect, if we are doing if we are doing a hard demodulation of the output, we are losing information, so our channel capacity decreases. So the loss in capacity compared to the previous case is around 1.13 dB. This is 10 log of 0.477 divided by 0.368, that's 1.13 dB. Now the third part of this question is as follows. There are 3 different sensible ways of converting this channel into a binary symmetric erasure channel. Now what is a binary symmetric erasure channel? So in a binary symmetric erasure channel, you have 2 inputs 0 and 1, and you have 3 outputs 0, erased output, and 1. So, one second, let me draw the model for binary symmetric erasure channel. So, let's say there's a delta probability of bits getting erased. Let's say there's an epsilon probability of bits being in error. So, this will be 1 minus delta minus epsilon, 1 minus delta minus epsilon. So, this is a binary symmetric erasure channel. Now, I am mentioning there are 3 different sensible ways to convert this original channel into a binary symmetric erasure channel. Now, what are those 3 different ways? One way is I club 0 dash, 0 double dash, 0 triple dash, 1 1 dash, 1 double dash and 1. I convert all of them into erase bits and I map 0 to 0 and 1 to 1. That's one way of doing it. Second way of doing it, I map 0 and 0 dash to 0, 1 and 1 dash to 1, and I map 0 double dash, 0 triple dash, 1 double dash and 1 triple dash. I map it to the erase bit. Or I could do 0, 0 dash and 0 double dash. I map it to 0, 1, 1 dash and 1 double dash. I map it to 1, and I map 0 triple dash and 1 double dash. I map it to the erase bit. So, there are 3 ways in which I can convert this particular channel into a binary symmetric erasure channel. Now, this question asks, find the capacity of the channel, find the capacity for the way that gives the greatest capacity. So, out of these 3 different ways in which we can convert this channel into a binary symmetric erasure channel, which one will give us maximum capacity? That's the first part of this question. And second part of the question says, find also the decibel loss compared to the 8 level demodulation and the decibel gain over hard demodulation. So, it's asking us to compute the loss in capacity compared to this original channel and gain in the capacity compared to the binary symmetric channel that we did in the problem 1b. So, as I said, this is our binary symmetric erasure channel. This is our erase bit denoting by delta, and these are the other received bits 0 and 1s. With delta probability the bits are getting erased, with probability epsilon the bits are getting in error. So, the probability of receiving the bits correctly is 1 minus epsilon minus delta. Now, this binary symmetric erasure channel can be decomposed into 2 strongly symmetric channel, the one which has input 0 and 1, the other which has this erase bit. You can see, if you look at this output 0, the transition probabilities here are 1 minus epsilon minus delta and epsilon. Similarly, if you look at this input, these transition probabilities are 1 minus epsilon minus delta and this is epsilon. So, 0 and 1 have the same focusing, so they can be clubbed together. However, its focusing is different from the focusing of delta, which is delta and delta. So, this is not a strongly symmetric channel, but we can decompose it into 2 strongly symmetric channel, one which has output 0 and 1, the other which will have output delta, and that is what we did here. We decompose it into 2 channels, one which has output 0 and 1, other which has this erase bit. Now following the same procedure, then we need to compute what is the selection probability of selecting this channel which has in output 0 and 1, which we denote by probability Q1. Similarly, we need to find the selection probability of selecting this channel whose output is this erase bit delta, and that is denoted by Q2, and these corresponding probabilities are similarly denoted by x and 1 minus x, and this is denoted by y. Now we will again check the transition probability of each of these outputs given input and compare it with the original binary symmetric erasure channel to get these probabilities. So we can see Q1 times 1 minus x is 1 minus epsilon minus delta. So if you look at probability of 0 given 0, this is given by Q1 times 1 minus x. This is Q1 times 1 minus x. And let us go back to the original probability of 0 given 0, that is this, that is 1 minus epsilon minus delta. So that's why we wrote Q1 times 1 minus x is 1 minus epsilon minus delta. Similarly, we can find out what's the probability of 1 given 0. This is nothing but Q1 times x. So this is Q1 times x. Now let's look at this original channel. Probability of 1 given 0, this is given by epsilon. So then epsilon is equal to this, and that's what we wrote here. So we have two equations. This is equation 1, this is equation 2, and we have two unknowns. One is Q1, other is x. We solve for it and we get the value of x to be this and Q1 to be this. Similarly, we can find out what is Q2 and y. Okay, we can find out that. So we do that, y comes out to be 1 and Q2 comes out to be 1 minus Q1, which is delta. Now the first set of channel, this channel which I am denoting by C1, this is a binary symmetric channel, so its capacity is given by 1 minus this, and capacity of this channel is 0. So we plug that in. This is the capacity of channel 1, where this crossover probability x is given by epsilon divided by 1 minus delta, and the capacity of the second strongly symmetric channel is 0. The overall capacity is given by Q1 times C1 plus Q2 times C2, which comes out to be this. Now as I said, there are three different ways in which I could combine the outputs. If I combine 0 triple dash and 1 triple dash to be delta, my epsilon in this case comes out to be 0.067 and delta comes out to be 0.242. So capacity in this case comes out to be this, and similarly for the two other cases I can find out the capacity. So you can see from here, out of the three ways of combining, this gives me the highest capacity. So what I do is I map 0 and 0 dash and 0 double dash to 0. I map 1, 1 dash and 1 double dash, I map it to 1, and I map 0 triple dash and 1 triple dash, I map it to delta. So if I do that, I get the maximum capacity, which is 0.31 bits. Now if we compare this with the capacity of the original channel, which was 0.477 bits, so there is a 0.44 dB loss. However, if you compare it with the capacity of the binary symmetric channel in problem 1b, there is a gain of capacity of around 0.69 dB. Okay. So let us look at this problem, which shows a channel with feedback. So we have a source U, bits are encoded into X, and this is fed to a discrete memoryless channel whose outputs are Y. But now there is a feedback from the output to the input. So the channel output is fed back to the input side. So now this selection of X depends also on what is being fed back. So subsequent selection of X depends not only on U, but it also depends on Y, which is the symbols which are fed back from the channel. Now we want to show that the channel capacity of this channel with feedback for a discrete memoryless channel with feedback does not increase channel capacity. So a capacity of a discrete memoryless channel is not increased by presence of feedback from the receiver to the transmitter. Then the question is, if feedback does not increase the capacity of a discrete memoryless channel, why should we do feedback from the output to the input? So let us prove this. Now just want to make a comment that if the channel has memory, then feedback can increase the capacity of the channel. However, if the channel is discrete memoryless, then feedback does not increase the capacity of the channel. So we want to prove that presence of feedback does not increase the capacity of this channel. So let's do that. So the mutual information between U1, U2, U3, Uk and Y1, Y2, Y3, Yn can be written using definition of mutual information like this. So this is joint entropy of Y1, Y2, Y3, Yn minus conditional entropy of Y1, Y2, Yn given U1, U2, U3, Un, which using the chain rule can be written in this particular fashion. So this is H of Y1, Y2, Yn minus H of Y1, Y2, Yn given U1, U2, Uk, and this using chain rule can be written like this. Now what I did was I further conditioned this on x1, x2, x3, xn. Now since I am further conditioning on x1, x2, x3, xn, so we know that this will be greater than equal to this particular term, with equality happening if xi would not. So we know that uncertainty in, let's say, A given B is more than equal to uncertainty A given BC, right? So that's why this term was larger than this term. So since we are subtracting a smaller term, I have written here greater than equal to. Now, what is the uncertainty in yn given y1, y2, yn minus 1 and u1, u2, u3, uk and x1, x2, x3, xn. Now, given x1, x2, xn, yn is independent of u1, u2, uk. So, I can write this as this. So, this then becomes joint entropy of y1, y2, y3, yn. You can see here, given xn, y does not depends on u. So, that is why we could write this like this. Now, using chain rule, I can also write this joint entropy as uncertainty in yn given y1, y2, yn minus 1, where n goes from 1 to n, minus this is coming from here. Now, from the definition of mutual information, this can be written as mutual information between x1, x2, xn and y1, y2, yn. Okay. So, what I have written so far is mutual information between u1, u2, uk and y1, y2, y3, yn is less than equal to mutual information between x1, x2, x3, xn and y1, y2, y3, yn. Now, proceeding further, I can write this mutual information between x1, x2, x3, xn and y1, y2, yn using chain rule for mutual information. I can write this in this particular fashion. So, I have applied chain rule for mutual information. So, I can write this mutual information in this particular form. Now, from the definition of mutual information, I can write it in terms of entropy. So, this can be written as uncertainty in yn given y1, y2, yn minus 1 minus uncertainty in yn given y1, y2, yn minus 1 and x1, x2, xn. Now, what is the uncertainty in yn given x1, x2, x3, y1, y2, yn minus 1? Now, note that we are talking about a discrete memoryless channel. So, what is the uncertainty in yn given xn, xn minus 1 and y1, y2, yn minus 1? It only depends on xn. So, then we can write this as uncertainty in yn given xn. So, this term comes as it is, and because it is a discrete memoryless channel, uncertainty in yn given xn and all other parameters, it will just depend on xn. Now, we can further simplify this term. This is entropy of yn given y1, y2, yn minus 1. Now, we know that conditioning cannot increase entropy. So, each of these individual terms will be less than uncertainty in yn. So, invoking that property, we can write this as less than equal to h of yn, and then we do it like this, we write it like this. Now, what is uncertainty in yn minus uncertainty in yn given xn? This, from the definition of mutual information, is nothing but mutual information between xn and yn, and we know what is the maximum mutual information between xn and yn or all possible input distribution, that is given by capacity C. So, this can then be written as equal to n times C. So, what we have shown is mutual information between ui's and yi's is less than equal to n times C. So, feedback from the output to the input does not increase capacity for a discrete memoryless channel. However, it does reduces the complexity of the encoder and decoder, and that's why we do commonly use feedback in our communication systems. Okay, let's look at the next problem. So Arjun is a meteorologist with a TV station, let's call it KTV. His record for predicting the weather in Kanpur city is given below. So this is what the actual happening. So this is whether the rain happens or whether the rain does not happen, and on this column I have the prediction of Arjun. So when actually rain happens and he predicts rain, that probability is 1 by 8, and when there is no rain and he predicts that rain is going to happen, that probability is 3 by 16. Similarly, when there is actually rain and he predicts that there is no rain, that probability is 1 by 16, and probability that there is no rain and he actually predicts it correctly, there is no rain, is given by 10 by 16. So these are his relative frequency of prediction. Now a student Amrita noticed that this weatherman Arjun is right only 12 by 16 times. He is right when he predicts correctly the rain happens, which is this probability, and he is correct when there is no rain and he predicts correctly there is no rain. So Arjun is right only 12 by 16 times. So is 3 by 4 times is correct and 1 by 4 times is wrong. Now she noticed that if he always predicts no rain, what is that probability? If he always predict, so he could be right 13 by 16 times by always predicting there is no rain. So if he predicts always there is no rain. Now Amrita explains her situation to an information theorist who is a supervisor. She explains this situation and applies for the job of weather forecast reporting. However, her supervisor Rakesh, who is an information theorist, he rejects her application. So you have to tell why Amrita's application was rejected, why her way of predicting the weather, which was right 13 by 16 times, was rejected by her supervisor, who is an information theorist. So the answer to this question lies, so we are going to look at actual weather and prediction as a input output relationship, and we are going to look at the capacity of such channels, and we will show that Amrita's channel gives less mutual information compared to the channel of Arjun, and Rakesh, who is an information theorist, that is why rejects the application of Amrita. So let us define a random variable x representing the actual weather. So when x is equal to 0, that means there is no rain, and when x is 1, it means rain has occurred. We also define another random variable, we call it y, and this is the prediction of the weatherman. So when y is equal to 0, that means the weatherman is predicting there is no rain, and when y is 1, the weatherman is predicting that there is a rain. Now if we view this weatherman as a channel that conveys some information about an underlying process, in this case the event is whether there is a rain or there is no rain, then we can define transition probabilities. So what is the probability that the weatherman will say there is no rain given there is no rain? What's the probability that weatherman will predict there is a rain when there is actually no rain? What is the probability that the weatherman will predict no rain when there is actually rain, and what is the probability of rain when there is actually rain? So we can use these 4 transition probability to describe this weatherman's channel, and similarly we could also define a priori probability of having rain or no rain. So we can compute probability of x being 0, which is nothing but, if we sum of this joint probability of x being 0 and y, we sum over all y's, that comes out to be 13 by 16. Similarly, probability of x being 1 comes out to be 3 by 16. Next, these transition probabilities for the Arjun channel we compute. So probability of y given x equal to 0 can be written as probability of x equal to 0, y equal to 0 divided by probability of x equal to 0, and that is given by 10 by 13. Similarly, probability of y equal to 1 given x equal to 1 can be written as probability of x equal to 0 and y equal to 1 divided by probability of x equal to 0, that is probability 3 by 13. And similarly, we compute the probability of y being 0 given x equal to 1, that comes out to be 1 by 3, and probability of y being 1 given x equals 1 comes out to be 2 by 3. So this is Arjun's channel. 1 denotes there is rain, 0 denotes there is no rain, this is actual value, this is a predicted value, and these are the transition probabilities. These are the a priori probability on x. So we can find out what's the probability of y being 0, that's 11 by 16, and probability of y being 1, that is 5 by 16. So if we use this to compute the mutual information, Arjun's channel is going to give us roughly 0.09 bits of information. Now let us look at Amrita's channel. Now what does Amrita's channel do? Amrita's channel always predicts no rain. So no matter whether actually there is rain or no rain, Amrita's channel always predicts there is rain. Remember, y denotes the predicted value, x denotes the actual weather. So this is Amrita's channel. So similarly, we could compute probability of y being 0 given x equal to 0, that is 1. This probability of y being 1 given x equal to 0 comes out to be 0. Probability of y being 0 given x is 1 comes out to be 1, and probability of y being 1 given x equal to 0 comes out to be 0. If we compute the probability of y equal to 0, in case of Amrita's channel, that's always 1 because she is always predicting that there is no rain, and probability of y equal to 1 is 0. So if we compute the capacity of Amrita's channel, that comes out to be 0. And this is the reason the weatherman's supervisor Rakesh, who was information theorist, rejected Amrita's application because her channel conveys 0 information, whereas if you go back and look at Arjun's channel, it gives 0.09 bits of information, and that's why Arjun's channel in the information theoretic sense is better than Amrita's channel. Okay, now let's look at next problem. So we have y1 and y2, and they are two random variables, and they are conditionally independent and conditionally identically distributed. So what do we mean by identical distribution given x? So what do we mean? Probability of y1 and y2 given x is given by probability of y1 given x into probability of y2 given x. Show that mutual information between x and y1, y2 is 2 times mutual information of x and y1 minus y1 y2, and use this relation to conclude that capacity of this channel is less than twice of capacity of this channel. So, mutual information between x and y1 y2, using definition of mutual information, I can write this as entropy of y1 y2 minus entropy of y1 y2 given x. Now, this joint entropy between y1 y2 can be written as uncertainty in y1 plus uncertainty in y2 minus mutual information between y1 y2, and this particular term, because given y1 y2 are conditionally independent, so uncertainty in y1 y2 given x can be written as uncertainty in y1 given x plus uncertainty in y2 given x. So, this term can be split into these two terms. All right. Now, we can take this term and this term. This is nothing but mutual information between x and y1, and take this term and this term. This can be written as mutual information between x and y2, and this we write as it is. So, mutual information, this comes out as mutual information between x and y1 plus mutual information between x and y2 minus mutual information between y1 and y2. This I can write as 2 times mutual information between x and y1 minus mutual information between y1 and y2. Now, let us look at capacity of channel with single look. So, that capacity is given by mutual information between x and y1, where we maximize mutual information over all input distribution. Now, let us look at this capacity of this channel with two independent look. So, we have just now showed that mutual information between x and y1 y2 can be written like this. Now, mutual information is greater than or equal to 0. So, then this whole term is less than or equal to this. So, this is less than or equal to 2 times the capacity of a single look channel. So, this proves our result that capacity of a channel with 2 independent looks is not twice of capacity of a channel with single look. Next, consider a pair of parallel Gaussian channel. So, we have 2 parallel Gaussian channel. First channel, the output y1 is given by x1 plus z1. For the second Gaussian channel, y2 is given by x2 plus z2, and z1 z2 is Gaussian distributed with this mean covariance matrix this. There is a power constraint which is given by expected value of x1 square plus x2 square is less than 2 times p, and let us assume that the first channel is bad compared to the second channel. So, sigma 1 square, which is the noise variance corresponding to the first channel, this is higher compared to the noise variance of the second channel. So, the question is, at what power does the channel stop behaving like a single channel with noise variance sigma square 2 and begins like a pair of channels? So, if you recall from our discussion on water filling algorithm, so if we have pair of Gaussian channel, we will start first pouring we will first start allocating power to the channel which is less noisy until So it will continue to behave like a single channel until it reaches a point when the sum of power and noise variance becomes equal to the noise variance of the second channel. So once that happens, then power will start getting distributed in both the channels. So this is very straightforward. So we will put all signal power into the channel with less noise. This follows from the optimal power allocation strategy until the total power of noise and signal in that channel equals the noise power in the other channel. And subsequently what's going to happen is we are going to split the power between those two channels. So the combined channels begins to behave like a pair of parallel channels when the signal power is equal to the difference of the noise power. So when this happens, it will start behaving like a pair of Gaussian channel. Now let us look at what is the mutual information for Gaussian generated random multivariate Gaussian random variable with distribution given by this. So let us compute the mutual information for various values of rho correlation. So as we are given that this is a multivariate Gaussian distribution random variable, so we know what is this entropy. The entropy of a multivariate Gaussian random variable is given by half log of, so here n is 2, so that will be 2 pi e square and the determinant of this covariance matrix. Now covariance matrix determinant is sigma 4 into 1 minus sigma square. So the joint entropy in this case is given by this expression. Now let us look at what is the differential entropy of these individual random variables x and y. This is given by half log of 2 pi e sigma squares. So the mutual information between x and y can be written as mutual information between can be written as differential entropy of x plus differential entropy of y minus joint differential entropy of x and y. This follows from the definition of mutual information. So we know the values of this, we also know the value of this. If we plug this in, what we get is mutual information is given by minus half log of 1 minus rho square. So let us compute mutual information for different values of rho. So when rho is 1, so when rho is 1, this is log of 0, so that would be mutual information will be infinite, right? And this agrees with the fact because x is y, x and y have complete information about each other. When rho is 0, this corresponds to the case when x and y are independent. So in that case we expect the mutual information to be 0. And similarly when rho is minus 1, that is then negatively correlated, x is minus y, then also we expect the mutual information to be infinite. Okay. So with this we are going to conclude our discussion on problem solving session. In the next class we are going to talk about rate distortion theory. Thank you.